Hi folks. So today we're going to talk about the alternating harmonic series. The alternating harmonic series is obtained by alternating the signs of the harmonic series. So if we put inside of sigma notation, say this power of -1 to the n plus 1, what we'll do is we'll generate alternating signs. So this series looks a lot like the harmonic series, except now we're alternately subtracting terms. So 1 minus a half plus a third minus a quarter and so on. And we wish to decide if the series converges. Actually, spoiler alert, it does converge, and we're even going to figure out, well, we won't figure out, but we're going to find out what the series converges to. So we can, as always, decide to look at some partial sums and see if we can glean any information from the sequence of partial sums. In this case, we can calculate them explicitly, and we could come up with decimal approximations. And we notice that the first term is 1, then we go down to 0.5, back up to 0.8, down to 0.58, and so on. They seem to be bouncing up and down. Perhaps what we should do is graph the sequence of partial sums. So you can do this using Desmos or a spreadsheet. And the graphical evidence here is promising. It looks like there may in fact be a limiting value for the sequence of partial sums. The question is, what would it be? And there seems to be a little bit of a window here where maybe these things don't converge. So let's try to figure out what's going on. And we'll notice a couple of things about this picture. If you looked at the first, the third, the fifth, and so on, if you looked at just the odd partial sums, they seem to be strictly decreasing. And similarly, if you looked at the even partial sums, that is the partial sums with indices 2, 4, 6, 8, and so on, it appears that the even partial sums seem to be strictly increasing. So let's see if we can prove this. So we claim the subsequence of odd partial sums is decreasing. So what would a proof look like? So we're going to set aside the alternating harmonic series here for reference. And the first partial sum is just 1. The third partial sum, that is to say the next odd partial sum, is 1 minus a half plus a third. Now, I'm not so interested in the fact that sigma 1 is actually 1. I'm more interested in the fact that sigma 3 is what you get by taking sigma 1 and subtracting off a half and then adding a third. And now if we factor out the negative sign, we can write sigma 3 as sigma 1 minus the quantity 1/2 minus a third, which, by the way, 1/2 minus a third is a positive number. And if you, let's see, that's 3/6 minus 2/6 is 1/6. So sigma 3 is sigma 1 minus 1 over 2 times 3. What's sigma 5? Sigma 5 is going to be sigma 3, the third partial sum, minus a quarter plus a fifth. We'll factor out the negative sign. And once again, we find that this new partial sum, sigma 5, is the old partial sum, sigma 3, minus a positive number. Similarly, with sigma 7. So what's the story? Generally, sigma 2n plus 1 is what you get when you take sigma 2n minus 1 and subtract off a positive quantity. So here's some odd partial sum, and here's the next partial sum. And so this, being this minus a positive number, means that your sequence of odd partial sums has to be strictly decreasing, because each new odd partial sum is obtained from the previous odd partial sum by subtracting off a positive quantity. So now we claim the subsequence of even partial sums is increasing. What's the proof look like? Well, it's very, very similar, and I'll leave it for you to do as an exercise. You can emulate the proof we just did, but you can show that the subsequence of even partial sums has to be strictly increasing. All right, now let's prove that the odd partial sums are bounded below. What do we mean by that? So we claim that if you looked at just the odd partial sums, there's some floor below which the values never go below. So how could we prove this? So first we're going to note that the even terms are all negative. And now we're going to let 2k plus 1 be an arbitrary odd natural number. And so what would the next partial sum be for sigma 2k plus 2? It would be the old partial sum, sigma 2k plus 1, plus the current term, which, because 2k plus 2 is an even number, that means we're subtracting something off. So any even partial sum is what you get by taking the previous odd partial sum and subtracting a positive number. So what does that mean? It means that odd partial sum has to be larger than the even partial sum. But that even partial sum has to be bigger than the original even partial sum, i.e. sigma 2. That's because the even partial sums by themselves are increasing, so sigma 2 will be lower than any other even partial sum. But now look what we've accomplished. 2k plus 1 was any old arbitrary odd natural number, and what we've proved is that that partial sum corresponding to that odd number is greater than sigma 2. In other words, the sequence of odd partial sums is bounded below by sigma 2. No matter which odd partial sum you're looking at, it's bounded below by sigma 2. Now, if we go back to our original graph, this is sort of clear in the picture because you've got your odd partial sums here and they're all bounded below by sigma 2. By the way, we could find a better bound, but it doesn't matter. We just wanted a bound, and that's what we were able to prove. We were able to prove that certainly sigma 2 does the job. So now we know that the odd partial sums are bounded below. And you can imagine what the other claim is going to be. The even partial sums are bounded above, and in fact, sigma 1 will do the job. So if you look at this picture, you can see what you'd be aiming for. You've got your even partial sums, and surely this term, sigma 1, is going to do the job of bounding all of those even partial sums. And the proof is going to look very, very similar, and I leave it to you as an exercise. Okay, here's a big moment. So we claim that the subsequence of odd partial sums converges by itself, and the subsequence of even partial sums converges by itself. And the proof of this is really simple, and it's going to rely on this very powerful theorem we've encountered before. So we've got the odd partial sums, which are strictly decreasing and bounded below. We have the even partial sums, which are strictly increasing and bounded above. And the monotone convergence theorem guarantees that both of these sequences have to converge to some limiting value. So where are we? We have the odd partial sums, sort of half the partial sums, are converging to some limiting value. Meanwhile, the even partial sums, which is sort of to say the other half of the partial sum sequence, is definitely converging to some limiting value. But what we haven't figured out yet is, are these two limiting values the same? If they're not the same, then we've got a problem if we're interested in this series converging, because clearly then this starts to look more and more like a sequence of partial sums that's just bouncing back and forth between two values, and that wouldn't converge. So the real issue is, are these two limiting values the same? So that's the next claim. The sequence of odd partial sums and the sequence of even partial sums converge to the same value. So what does this proof look like? Let's just take the difference of these two limits. And we'll notice that there's a limit law that allows us to just take the difference of these and look at the limit. But the difference between successive partial sums is just the term that you're adding, and we know that the limiting value of 1 over 2n plus 1 is 0. And what does that mean? It means these two limiting values are equal. So the answer to our question is a resounding yes. So there is in fact just one common limiting value to which the odd partial sums and even partial sums are both converging. So what does that mean? Put those together and you realize that the alternating harmonic series has to converge to some limiting value L, because the sequence of partial sums is converging to some value L. And the partial sums, just by the way this worked out, they alternate between being greater or less than the value of L. And we know that because one of them is strictly decreasing and the other one strictly increasing. They're on separate sides of the limiting value. So these partial sums alternate between being larger or smaller than the limiting value of the series. So let's just look at some numerical examples. Here's the 100th and 101st partial sum of the alternating harmonic series. So we know from what we just discussed that the actual limiting value lies somewhere in between. Now, based on this numerical evidence, L could be 0.69 or 0.70 to the nearest 0.01. It depends, because we don't quite have enough information here to know how to round to the nearest 0.01. So what we could do is push further and calculate the 1000th and 1001st partial sum. And based on this evidence, we can see that at least to the nearest 0.01, it's definitely going to round to 0.69. So we could decide to push for more accuracy. Let's calculate the 10,000 and 10,001th partial sums. And, let's see, how much accuracy can we sort of guarantee here? Well, it looks like we can round to the nearest 0.001. Beyond that, it's really hard to say how this is going to round. And So what's the situation here? We went all the way up to the 10,001st partial sum, and we've got no better than 0.001 accuracy in our estimate of the limiting value. What's going on? So if you zoom in on the sequence of partial sums, you can see that what happens is this sequence of partial sums is really dithering. It keeps bouncing back and forth as if it's not really, can't decide where to go. And so it's really hard to take the evidence here from these partial sums and sort of get a good estimate of the limiting value. What I'm about to do is not too supported rigorously, but we might imagine that if you just average successive terms, you could get at least a decent estimate of the limiting value. So we could just concentrate on these last two terms we took, and if you average them, you'll get about halfway, and hopefully this would be close to the limiting value. We have no real rigorous way of asserting this is the case, but here are the two partial sums we were just looking at. And if you take their average and carry out that calculation to this many places, you get a guess for the limiting value to be this. Now, if you've worked with logarithms recently, you might recognize that this is pretty close to the natural logarithm of 2. That's pretty good agreement. And here's the fun fact. The alternating harmonic series does, in fact, converge to the natural logarithm of 2. So this partial sum sequence that we see is actually bouncing back and forth around this limiting value of ln of 2. It seems to be taking its time getting there, but in fact it does converge to the natural logarithm of 2. Now, a few comments are in order. The convergence is, in fact, slow. This would be a terrible way to actually approximate the value of the natural log of 2. It's not a winning strategy because n would have to be enormous for the partial sum sigma n to be at all close to ln of 2. So it's just a lousy way to crank out the numerical value of ln of 2. The second comment is that the limiting value was discovered in the 17th century by several mathematicians working independently, Newton among them, Mercator, and it's probably fair to say that actually this isn't a case where the series was floating around and people wondered what it converged to. Logarithms were being developed and refined in the 17th century, and I think it's fair to say that actually the series arose as a theoretical way to calculate ln of 2. It's sort of a case of working the other direction. And Leibniz generalized the proof you just saw to extend to a more general case, and it's the so-called alternating series test, which will be a subject of a future video. And I want to point out one last thing, which is really important for you to imagine for general series. The harmonic series itself diverges to infinity. One way to think about this is if you looked at the terms and stacked them up, if you imagine partial sums being just taking that many steps to the right, well, the series diverging to infinity means you keep drifting to the right indefinitely. You're just going to march off to infinity if you're patient enough. But here's the weird thing. If you alternate half the signs, you converge. You converge to ln of 2. So what's happening here is we're taking every other term and we're reversing the direction that we're stepping. And by doing so, you now have a series that converges, and it converges to ln of 2. And one very last comment. These two series also have in common the fact that they're slow to get to their fate. The harmonic series is slow to diverge to infinity. You have to take partial sums sigma n, where n is enormous, to get the sense that it's growing large. And similarly, you have to take enormous values of n to get sigma n to look at all like ln of 2 in the case of the convergence. So this is weird because both the divergence and the convergence of these series are both relatively slow.